Do it. What was I saying? Yeah, unique means what? Say it again, Kieran.
To yourself, nothing else has it.
Right, nothing else has it. So, hydrogen in that gas tube actually looks like that. So there's hydrogen. What are those numbers?
410.139.
Yes, that's what they are, but what do they mean?
46.0.
The speed.
That is the distance between them.
Not frequency.
The distance between the wavelengths.
The wavelength, right. So,
I just
red,
said that 4 times.
stop talking so much. Red is usually in the 600s, okay? Violet's down in the 400s, and then, I mean, that's in 400 too, the blue, but there's a range there from, you know, pretty much 700 down to 400. That's your range. This is not continuous. How do you know? It's choppy. You see the lines. That's bright line spectrum, okay? That's hydrogen. It only has those 4 wavelengths. That's it. Oxygen.
Wait, what are the numbers?
Oh, I didn't really fully. They're the wavelength, but I didn't fully explain.
Yeah.
Those are wavelengths in nanometers. Nanometers are a really small measurement. It's 1 times 10 to the negative 9th meters thick. So really, really small.
What?
So that's the length of the red light there, the blue, the violet. And the confusing part, and it's hard for me to really fully explain this, I admit, maybe I need to get better at it, but violet has all types of different wavelengths. So that one there and that one there, they're both different shades of violet. So one's at 410, one's at 439.9. So I sometimes don't do a good job explaining that to kids because they think there's only one line for one color. There's lots of different lines for each color. It's just the elements don't use them all. They don't produce all of them. Let me give you an example. Oxygen looks different. There's oxygen. It's harder to see. It's kind of faint, but it has multiple lines of yellow, multiple lines of whatever that is, teal, multiple blues, hard for you to see. So that's what I mean by it's unique. Oxygen looks like this. Hydrogen looks like that. No other element looks like those. They're unique. Yes?
If they have all of them.
What do you mean? Oh, you mean like that?
All one
Oh, so in lab, what I'm going to do is have about 8 of these things plugged in, maybe, yeah, 6 to 8 of those plugged in. You're going to go around with the spectroscopes, and you're going to see these in here. And you're going to try and color these with colored pencils on paper. So the kids always say, oh, this one has, you know, like 6 yellow lines. Which one do I put? That's kind of what you mean, right?
All of them.
I always say the brightest ones. So if you're looking at a whole bunch of lines, there's usually ones that are obviously brighter, so we'll just put those down. It is kind of arbitrary.
Are there ever
I like
ones
that
have
one.
like the entire
Like the entire orange section
Yeah.
with lines. Yeah, helium has a lot of lines, so
So how do you
very carefully.
Wow.
I guess I don't have a great answer. It kind of depends on the student and what they see and how they can interpret that. So I don't really grade that too heavily. So anyways, that's oxygen. There's hydrogen. All right. Now on that homework, it's going to give you those lines on paper, and it's going to give you maybe 4 of these, and then there's going to be a 5th one that says unknown. And what you have to do is, like you do in lab, you're going to match them up. So if I look at that hydrogen spectrum and it matches that, but I don't know that's hydrogen, I can infer that it is hydrogen because it looks just like the one I have on the board. So you're basically looking at what you know and comparing to what you don't know. So the homework will help you with that. All right, it's no point doing a question in class. So anyway, there's oxygen, hydrogen. These are unique. Every element is unique. How is that useful to astronomers?
You can see what stars are made of.
Very good, Kieran. Yes. Now, astronomers don't just sit at telescopes and look at the stars. They actually never look in telescopes. For example, the Hubble telescope, do you know where that is?
In space.
Right, so you can't sit there and look through it because it's in space. So how do we get images from it?
Computers and the satellites.
Yep, satellites, computers, right. So it transmits the images back to us. So anyways, a lot of, basically every telescope that we have across the world and in space has fancier versions of this. So when you point the telescope at an unknown star, planet, or whatever, these things get spit back to us and we can figure out what elements we're looking at. That's how this is useful. All right, it's kind of cool. You'll be doing a scaled down version in lab. All right, so that's called the bright line spectrum. Questions on spectrums or spectra?
No.
What is your deal?
When you picked up the thing, you were like,
Yeah, okay. I stuttered a little bit. Yes, I talk a lot. Sometimes that happens. Right, Morgan? Sometimes stuttering happens.
Yeah.
Yeah.
It was just funny the way you did it.
Yeah, all right, good. Get over it. Okay, so bright line continuous. Do we understand the difference, hopefully?
Yes.
C.
Olivia, you with me?
Yeah.
Good.
Yeah.
Elena?
I'm full with you.
Good. Jake? Good. All right, so I think we're good with that. Let me consult my notes to make sure I'm not forgetting. I feel like I'm forgetting something here.
Probably.
Radioactivity.
No, that's not today.
Water break.
Free time.
No, that's crazy talk. We got
No.
electron dot diagrams
That's
to learn
pretty
about.
Used to crazy talk.
I am forgetting something. What is it?
Knowledge.
No. All right, let's watch these videos. Here we go. All right, lights, please.
Oh, Autumn's not in here. I guess.
Yeah, you can get those. Thanks.
Okay. I'll get ready to go for it.
All right, so I'm not going to play the sound with this because the guy starts talking about things that'll confuse you, but this is an analogy of an electron going from the excited state down to the ground state. However, here's the confusing part. See where it says ground state?
Yeah.
Okay, the ball represents an electron. Now, that electron doesn't ever come down here. So, what you learn is 100% correct, not lying to you. It gains energy, jumps up, higher level, falls back to the ground state, and releases light or spectrum. But in a hydrogen atom, that's what this is replicating. The one electron hydrogen has, when it falls from the 6, if it goes back to the first level, it gives off light we can't see. What can we see?
Visible light.
Visible light. We can't see X-rays, we can't see radio waves, we can't see cosmic rays, gamma rays, microwave. We can't see any of that. So this is called the Balmer series, which you don't need to know. But when the electron goes from the 6th to the 2nd, 5th to the 2nd, 4th to the 2nd, 3rd to the 2nd, it gives off these different colors of light. And the higher it falls, that's higher up on this color chart here. So violet is when it falls from the 6th, and then when it falls from the 3rd, that's red. You don't need to know really any of the details here. I'm just explaining what you're going to see. What you do need to understand is the process. It becomes excited, falls back, releases that light, and that's how spectrum is produced. So that's what you're going to see. It just keeps doing it over and over again. So from 6 to 2, that's one wavelength of violet. That's one wavelength of blue, one wavelength of green, and then one wavelength of red. So that is the spectrum for hydrogen, and it's just representing it with a ball on stairs to give you a visual of excited back to ground. Excited back to ground. Again, in hydrogen, it can fall here, but we can't see that. It's not called visible light. It's like X-rays. So it's different. You can't see that. So again, this is just a very obvious example of what I've been trying to teach you the past couple days. Okay, so excited, down the ground, and it gives off that photon of light, and we're not watching whatever that is.
You have to take cancer.
Quick.
I understand that. All right,
Oh
we're done with that
no.
anyway.
Oh god.
Okay. Oh, you know what that is?
It's those light bulbs that go in there.
Wow.
Oh, he's got this
What's he gonna
taser
do?
stick.
Okay.
Got the taser
What's
stick.
he gonna do?
Is that gonna work?
Oh, see, now he's interested.
Oh, there's math.
He's like, oh,
This is how my YouTube probably started too. Yeah.
I wonder how. Just instantly reads it.
I think you missed the part where he actually
Okay.
Explained it.
did it.
In your notes, I want you to write electromagnetic spectrum. You guys know what this is?
My pen's dead.
Electromagnetic
Oh, my
spectrum.
What is it? Where does it come from?
Electron.
It comes from the sun. So the sun and all of the light coming at us is coming, or is called, sorry, electromagnetic spectrum. Every form of light is on this thing. Every form of light. X-rays are forms of light. You may not know that, but it is. Different than the light we can see, but it's a form of light. Okay, we see visible light, gamma rays, microwaves, radio waves, all forms of light on the spectrum. So let's write this down here. Give me one of these things here. Whatever you want to call that. On this end, we're going to write gamma rays, cosmic rays. Next to that, put X-rays, UV rays, ultraviolet, right?
We're putting stuff on top of the thing.
Nope.
Uh-oh.
Over here, we're gonna have radio waves.
Oh, jeez.
So over here on the left side, we're gonna have very small wavelengths. Very small wavelengths. Over here, radio waves, very large, or just large wavelengths. And then in the middle, let's see, I think microwaves would be kind of like,
Yeah.
microwaves. Trying to think of enough. Infrared is somewhere in here. What's infrared?
It's what they use to see, like, blood splatter.
Wait, Sam knows.
Oh.
You have a thing
It's the scope
Fire
of Call of
department.
Duty.
Yeah.
where you look through it and you can see different colors based on heat. That's what infrared is. You can see the areas with lots of heat give off lots of infrared waves, and it's like orangish red, right, on
Yeah.
the screen.
Red is
Yeah.
really
And then
hot.
if it's cold or a lack of heat, then it's blue.
Purple.
It's the
Purple,
scope
right,
of Call
yeah.
of Duty.
So it doesn't have those.
That's how I know.
All right, so this girl, I think, has a weird accent. She says football field and wavelengths very strangely.
Is that a
So I'm
problem?
just telling you so you don't, start laughing and lose
Oh,
focus.
it's
I'll actually probably
So
start
just
laughing
be
anyway.
expecting it, all
I'll
right?
be expecting it.
Try to
Wait, how
stay
did you-
focused here. So this is the best short video I could find on electromagnetic spectrum. It's pretty good. It's pretty good.
Monkey.
Hi, I'm Emerald Robinson. In this What Is video, we're going to take a closer look at the electromagnetic spectrum. What we see as light is only a small part of the electromagnetic spectrum. The electromagnetic spectrum refers to the many types of radiation released from stars, including our own sun. Electromagnetic radiation travels in waves. Frequency describes how many waves per second a wavelength produces.
Now, I don't like what they just did there, where if you watch, it's blinking, then it's blinking faster.
Magnetic spectrum refers to the many types, including our own sun. Electromagnetic radiation travels in waves. Frequency describes how many waves per second a
So that implies that these things are moving faster or slower. If you have a really big wave with big wavelength, it's still moving like this, still moving the same speed as a wave that's very close together. So it has really sharp.
The bumps are going, more bumps are going.
Right, so frequency, if we have a line here on the board and we have a big wave, every second, how many of these peaks pass that point, that's called frequency. But if you have a big wave, it's going to have a really low frequency because it's going to take a little longer for these peaks to pass because they're so spread out. But if you have waves that are short, like these, short wavelengths, okay, and they're huddled together like this, when they pass that point, a lot of them, many of them, will pass this line here in 1 second because they're so close together. That has a high frequency. It's how many peaks pass that in 1 second. That's not a regions thing. You don't need to know it or memorize it, but that's what that word means. How many peaks pass a certain point in 1 second? You guys ever hear of hertz or megahertz?
Yeah.
Like radio frequency, that's what it comes in. That's what it means. So the bigger that number, the more waves pass a point in 1 second. So that's frequency. So the bigger the wavelength, the smaller the frequency. Smaller the wavelength, the bigger the frequency, the higher the frequency.
wavelength produces. Wavelength measures the length of an individual wave in meters. Scientists describe the electromagnetic spectrum as a long line. At one end lie radio waves, with the longest wavelengths and lowest frequencies in the spectrum. A single radio wave has the length of a football field. After radio waves come microwaves, which produce more energy due to shorter wavelengths and higher frequencies. Cell phones, radar, and microwave ovens use microwaves. Next comes infrared light. The sun.
Do you know why microwaves are called microwaves?
Because they cook your food and you put it in for 30 seconds. It sounds like World War IV is going
None
on.
of this makes
And you
sense.
get the middle and it's freezing cold.
When was World War III exactly?
Exactly.
You said World War IV.
Exactly.
As if 3 has already occurred.
It was the
Did I miss
3
something?
went on with your cousin's meal. Now it's yours.
Alright. That's
And it's still cold in the middle, even though the microwave's warmed up.
Circle it. It warms evenly.
yeah.
I'm too lazy to do that. I put food on a plate,
cut it
throw
up
it in there.
smaller
It's
pieces.
cold.
But anyways, it was a joke what I was getting at. Microwaves use microwaves to cook the food. And so do cell phones. Cell phones use microwaves as well to communicate. Now, radioactivity actually is when things emit light waves as energy. So we're going to talk more about that in a little bit here.
On fire, living creatures and other heat sources all produce infrared light. While we cannot see infrared light, we feel it as heat.
I'm focused.
Visible light occupies a narrow slice of the electromagnetic spectrum, nestled between infrared and ultraviolet light.
So that's the only thing we can see. You can't see gamma, cosmic, X-rays, ultraviolet, radio. You can't see any of that. So if you're those numbers, I don't know if she's going to zoom out again, but the difference in size, there's so many different forms of light. We can only see, where is it? Right here. Okay, that's visible. That's the only little area that we can see with our eyes. Which again, I said before, I don't know if it was in here, I think that's a good thing, because if you could see everything, I think it would be very difficult to see anything because it would be so busy. But I don't know, because then you said the other day, well then you wouldn't know any different. But yeah, you're right.
What?
But
You don't
never
remember
mind, you
it?
don't remember. You say so much, you don't remember what you said.
Yeah, that's right.
So this is what we can see, and again, red has the biggest.
Red wavelengths have the lowest frequencies and longest wavelengths of
700
visible light.
down should be about
As you
400.
move from red through orange, yellow, green, blue, and finally violet, wavelengths shorten and frequencies increase. From visible violet light, we move into ultraviolet frequencies. Human skin produces vitamin D when exposed to ultraviolet light, but excessive ultraviolet light causes sunburns. Next, X-rays, which pass through soft tissue but not denser materials such as bone, making them valuable for medical tests. X-rays also have security applications such as airport baggage checks. Gamma rays produce even shorter wavelengths, higher frequencies, and more energy in comparison to the football field size.
So, what's the problem with these down here for us?
They
Wait,
cause
wait,
cancer.
what?
Yeah, they can cause cancer, they screw up your cells. So, I don't know if you guys know this, but if you for some reason keep hurting yourself and you have to keep getting x-rays, eventually the doctors will say, we have to wait. You have to wait, whatever, 6 months before you get another x-ray or do another test, because you can't be exposed to, there's like a level, I forget what it is, but you're not supposed to be exposed to a certain amount of radiation in a certain time period, which makes sense because it causes cancer. So yeah, that's why we wear sunscreen to block ultraviolet, but apparently if you're in the sun, I don't know, I think it's 8 to 10 minutes, I could be wrong, don't quote me, that's good to get the vitamin D, then put the sunblock on. Yeah.
So, what if you're like traveling all the time?
Right. I don't know. I mean, I would not feel too good about that.
I get
but,
sunburn in literally 2 seconds of being outside.
Right. Yeah, I'm with you. I'm pretty pale as well.
Thank you.
Well,
So,
there are some places in the world where then you're gonna have to constantly wear sunscreen because
thanks, Karen. Yes, like people who live around the equator, perhaps.
Yeah.
that place.
However, a lot of people who, if they've lived there their whole life and were born there, usually a different
What if you're a
ethnicity
foreigner
than us, for
from
example, their skin can handle it better than we can because we're
Yeah.
from the north. But anyways, back here.
Iceland.
So yeah, this stuff here, radiation, okay? Radioactivity. Hey, stop. So this stuff here we're going to be talking more about with nuclear chem, which is the next unit in terms of radiation. So for a long time I didn't do a good job explaining what this is. This is just every form of light coming at us from the sun, from space, and it's also in this room, the electronics, cell phones, and that some people say don't sleep with it next to your head. Because, like if you have a nightstand, because there isn't long-term studies about the radiation coming off here, the waves coming off of here, microwaves, and if they're going into your brain, what that's doing. Okay?
Really?
Yeah, and some people won't carry them in their pockets. All right, male or female, you got reproductive stuff going on down there. So, but all seriousness, who knows? I don't know what it's doing. So, I carry mine in my pocket, but. Anyways, just throwing that out there, that there's a lot we don't really know about some of this stuff and how it affects us too. All right, so anyways, that's the electromagnetic spectrum. So when electrons gain energy and fall back to ground state, they give off light, but they also give off this stuff too. Okay, there's other things besides what we can see. All right, last couple minutes here. Lights, please. I'm going to introduce something. We'll finish it tomorrow.
Radioactive.
Electron dot diagrams.
Sounds so fun.
It is extremely fun. Electron
I was just explaining.
dot diagrams. Here we go. So all I got to with period 2 is just barely got them down on the board, and the bell rang. We're about the same spot here. So Lewis figured these out, or just developed these, or came up with this idea. So they're sometimes called Lewis dot diagrams. And what it is using the valence electrons as dots to show chemical bonding. So I introduced this now. We don't learn bonding until after nuclear. So my goal is to get done with nuclear, or pretty close, before break next Friday. And then when we get back, kind of review it a little bit, obviously, and then get into bonding. But it's important just to learn it first. So that's why we're doing it now. So here's what we're going to do. Across your page from left to right, I want you to write Na, Mg. We're going to go right across the third period there. Al. Leave a little space between them.
Oops.
Don't put them right on top of each other.
G. A. L. S. I.
So I'm just going to show you what a dot diagram looks like, and then it'll make no sense, and then we will learn tomorrow more about it.
Nice.
Okay. How many valence electrons does Na have? Kristen. I'll give you hints in group 1. 1. So it gets 1 dot right here. Andrew, how many valence electrons does Mg have? I'll give you hints in group 2. 2. 1 here and 1 there.
What?
How many dots does aluminum have, Nick? 3. 1, 2, 3. How many dots does Si have, Sam?
4.
4. 1, 2, 3, 4. We'll pick up the rest of it tomorrow. But I'll give you a hint. It goes in order.
That's crazy.